When people imagine nanorobots, tiny machines built from molecules or nanoscale components, they often think of them as passive tools, delivering drugs, repairing tissues, or cleaning up pollution. But what if these nanobots could learn? Artificial intelligence at the macro scale already shows us how machines can be trained on data, improving their performance with each iteration. Could a similar approach one day be applied to nanobots so that they adapt in real time to their environment, becoming not just tools, but intelligent agents? Doesn't it sound like science fiction and yet feel almost inevitable given the trajectory of both nanotechnology and AI? At first, nanobots would be trained indirectly, much like today's AI algorithms. Simulations at the molecular scale could model billions of possible motions, reactions, and interactions. Machine learning could then identify which strategies best allow nanobots to navigate chemical gradients, avoid obstacles, or assemble structures. These training regimes would not occur inside the nanobots themselves at first, but in virtual environments where designs are refined. Once optimized, the nanobot's structure or control scheme could be imprinted, hardwired, into chemistry, mechanics, or surface reactivity. Isn't it fascinating that intelligence at this scale might begin as embodied physics, rather than circuits or code? In later generations, nanobots might gain real-time adaptability. Imagine nanoscale sensors detecting pH, temperature, or chemical signals, and actuators responding through changes in motion or catalysis. Reward for learning principles, rewarding useful actions and discouraging harmful ones, could be encoded physically so that nanobots learn behaviors over time. For example, a drug delivery nanobot might learn which pathways reach tumors most effectively while avoiding healthy tissue. This would not be intelligence as we know it, but a molecular-level analog, a feedback loop where environment shapes behavior. Could this be the first step toward nanoscale autonomy? A lesser-known frontier is swarm intelligence. Nanobots may be too simple individually to be smart, but collectively they could mimic the behaviors of ants, bees, or flocking birds. By following simple local rules, attraction, repulsion, alignment, swarms of nanobots could self-organize into complex patterns, repairing tissues, building materials, or exploring environments at scales no single bot could master. AI already uses swarm-based algorithms. At the nanoscale, those same principles could become embodied in matter. Would intelligence then emerge not from one nanobot, but from the choreography of millions? The paradox is clear. Nanobots are envisioned as the smallest of machines, yet their future may lie in becoming intelligent systems trained like AI to adapt, evolve, and self-organize. Out of rigid molecular design could emerge flexible nanoscale problem solvers. The question is whether we will control this process or whether once nanobots learn to learn, they will chart their own paths, just as larger AI systems sometimes surprise us. The haunting possibility is that the first truly intelligent life beyond biology may not come from giant supercomputers, but from swarms of tiny nanobots learning silently in the unseen nanoscale world. Would that make them our creations or our successors? Current nanobots are largely passive. Following predefined chemical or physical rules, they move by catalytic reactions, magnetic fields, or acoustic waves, but lack adaptability. Training them like artificial intelligence would mean giving them the ability to adjust behaviors based on feedback. This requires nanoscale sensors, memory elements, and reprogrammable responses. Instead of just moving, they could learn optimal navigation in complex environments. Intelligence at this scale is not about thinking, but about adaptive pattern recognition. It bridges the gap between machines and autonomous agents. The leap is from mechanical execution to responsive learning. Catalytic nanomotors that only move forward could be adapted to reverse when sensing toxins. It is like teaching a dog tricks. The same body can do far more when trained with feedback. Artificial intelligence thrives on training through data and reinforcement. Nanobots could be designed to mimic this, adjusting chemical pathways or motion patterns depending on stimuli. Reinforcement could come from energy efficiency, task success, or binding targets. By linking nanoscale feedback loops with molecular switches, nanobots could learn at the population level. Millions of bots acting together would refine behaviors like an evolving neural network. The AI paradigm becomes chemical and physical rather than purely digital. Training would be embedded in the material itself. This creates intelligence without conventional computers. Swarms of nanobots could collectively learn optimal drug delivery routes inside tissues. It is like bees learning the best foraging paths through repeated exploration. For learning to occur, nanobots require a way to store information. This could be achieved with molecular switches, conformational states, or embedded DNA logic. Nanobots could remember previous encounters by changing their surface charge or catalytic state. Such memory would allow adaptation over time rather than repeating identical behaviors. These memory units function as nanoscale analogs of synapses in the brain. Combined with feedback, they turn chemical machines into adaptive learners. The design principle is to encode training into molecular structure. Memory makes nanobots more than mere machines. DNA, nanodevices, can toggle between states based on past binding events, effectively remembering inputs. It is like footprints in sand. Each step leaves a trace that guides the next. Individual nanobots are too small to hold complex intelligence, but collectively, millions can act as a distributed AI system. Through local interactions and signaling, swarms could self-organize into functional patterns. Training emerges at the group level, where collective outcomes are rewarded or reinforced. Swarm intelligence parallels neural networks, where no single unit is intelligent, but the ensemble is. Adapted swarms could repair tissues, attack pathogens, or build nanoscale materials. The intelligence lies in emergent behavior, not individual machines. Nanobot swarms thus embody AI principles in matter. Magnetic nanobots already form swarms that align into chains. Adapting their configuration dynamically, it is like an ant colony. No single ant is smart, but the colony solves complex problems. Nanobots could be trained through artificial evolution. Populations of bots with small variations would be tested in tasks, with successful variants amplified. Over many cycles, efficient behaviors would dominate. This mirrors reinforcement learning at the material level. Environmental feedback acts as the training dataset, shaping nanoscale design. Instead of coding intelligence, evolution discovers it. Such training would allow nanobots to adapt beyond what human designers foresee. It embeds intelligence into evolutionary dynamics. Nanoparticles selected for binding cancer cells evolve higher specificity after iterative screening. It is like breeding dogs over generations for better herding instincts. Future nanobots may not be trained alone, but guided by AI at larger scales. Cloud-based algorithms could control swarms, while bots supply data from the nanoscale environment. Machine learning models refine strategies and transmit updates back to the swarm. This creates a hybrid loop. Macro-scale AI trains nanoscale machines. Over time, nanobots may autonomously refine strategies themselves. Human input, AI design, and nanobot execution merge into a single adaptive system. Intelligence becomes distributed across scales. AI-guided nanobots could adjust cancer drug delivery in real time based on imaging and patient data. It is like a conductor guiding musicians while they also improvise together. Training nanobots to act autonomously raises serious risks. Poorly controlled bots could adapt in unintended ways, causing harm. Intelligent swarms might evolve resistance to shutdown protocols. Ethical frameworks are needed to balance innovation with safety. Transparency in programming, built-in kill switches, and environmental safeguards will be essential. Without such precautions, adaptive nanobots could pose ecological or medical threats. Their intelligence must remain bounded within human oversight. The challenge is to train without losing control. Concerns mirror fears of engineered bacteria escaping containment and evolving independently. It is like teaching a child independence, but still needing rules for safety. If mastered, intelligent nanobots could transform medicine, energy, and materials science. They could seek out and repair cellular damage, deliver drugs with unprecedented precision, or clear arterial plaques. In industry, they could assemble nanostructures atom by atom, enabling quantum devices and advanced materials. Environmental applications include breaking down pollutants or harvesting trace resources. Their adapted intelligence allows operation in unpredictable conditions. This flexibility makes them more powerful than static nanomachines. Intelligent nanobots would be a technological revolution. Nanobot swarms could autonomously detect and neutralize viral particles in a bloodstream. It is like sending an army of adaptive scouts into unknown terrain who can improvise as they go. The paradox is that training nanobots, like AI, blurs the line between matter and mind. Machines once seen as passive become adaptive, almost lifelike. Intelligence arises not from large brains, but from nanoscale physics coupled with feedback. Yet the more intelligent they become, the harder it is to maintain human control. Nanobots could be both our most powerful medicine and our most subtle risk. The challenge is not only to build them, but to guide them responsibly. In merging AI with nanotechnology, humanity steps toward creating a new form of artificial life. The question is whether we can train it or whether it will begin training itself. Intelligent nanobots that repair DNA mutations could also evolve new pathways unintended by their designers. It is like teaching fire to cook food while knowing it can also burn down a city.